So the second derivative test is not about concavity at all. It's about whether or not the critical numbers are actually maximums or minimums. So it's a way to figure out extrema without doing the sign test. That's basically what it ends up being. If you don't care where the function is increasing or decreasing, or if I just give you critical numbers, if I gave you critical numbers in a second derivative, you don't know what the first derivative was. And actually, there's no way that you can determine what the first derivative was. Because what's the derivative of a constant? 0. So the first derivative might have had it. For example, if y prime was, say, x squared plus 50, y double prime would be 2x, right? So the problem is if y squared, or if y prime was equal to x squared plus 1, what's y double prime? 2x. It's the same thing. But that constant's going to make a huge difference when we're trying to figure out a sign or when we do our sign test. So if I give you critical numbers and a second derivative, there's no way you know what that constant was. So we say to ourselves, all right, we got to figure out a way to do this. How are we going to be able to actually say, all right, how can I use a second derivative to figure out extrema? And it's actually pretty simple. So all you do is, 1, you need critical numbers. And 2, you need the second derivative. And I'll call the critical numbers C. Now, if f double prime at C is greater than 0, the function that we're dealing with, f, has a minimum at x equals c, or you can think of c comma f of c. So this ends up being one of those counterintuitive math things. You know how every once in a while you think you'd have to add, but then you end up subtracting? Or if you're trying to figure out a vertex of a parabola, you would think it would be x plus 2 if the vertex is at x equals 2, but it ends up being you'd put in x minus 2 and all that. Same thing here. It's counterintuitive. Usually we'd say, well, we'd have a maximum if it's bigger than 0, but if we're looking at the second derivative, it flips it on it upside down. If it's less than 0, or if it's positive, if the function's positive, then we know it's a minimum. If f double prime of c is less than 0, what do you think it has? Yeah, f has a maximum. Oh, that's a good thing I did that too. So that would be the point. If we're looking at a critical value, and that's the point. Now, if f double prime of c is equal to 0, we can't tell. It might be a maximum. We need to use a first derivative test at that point. And Sometimes you know, sometimes you don't know. Now, let's say I gave you the function f double prime of x is equal to 4x minus 1, and my critical values, or critical numbers, are 1, or negative 1, 0, 1, and 6. I'd hate to see the function that gave you those values. But, hey, there are functions like that all the time. Now, how can we figure out if these are going to be minimums or maximums? Yeah, just plug them in. See what you get. What's f prime at negative 1? You get negative 4 minus 1, which is negative 5. So is this going to tell me we have a minimum or maximum? It's a maximum because it's negative at x equals negative 1. Now, if f prime equals 0, we're going to get 4 times 0 minus 1, which is a negative 1, which means we have a maximum at x equals 0. Example. This is an example. You might not. It could be a weird function that has an asymptote in the middle of it. So we don't know what the function was. That's the cool thing about this, is you don't know what the original function was. You just go with what the test gives you. Because there could have been an asymptote that cut that graph off right in the middle, and you have a maximum on both sides. So, like I said, I'd hate to see the function that gave you these values. Because who knows? F double prime at 1, 4 times 1 minus 1. That's 4 minus 1, which is equal to 3, which is positive, which means it has a minimum at x equals 1. And then f double prime at 6. So it's 4 times 6 minus 1. That's going to be 24 minus 1, which is 23. That's positive. So when it's positive, you get a minimum at x equals 6. So in order to figure it out, the points themselves would be negative 1, f of negative 1. 0, f of 0. 1, f of 1. Well, what happens if it was 0? What if, let me give you another one. How about this? 1/4 is a critical number. F double prime at 1/4 is going to be equal to 4 times 1/4 minus 1. Well, what's 4 times 1/4? 1. So I get 1 minus 1, which is 0. Which is undetermined. So at that point, we don't know. So that would be the case for an undetermined critical value, or undetermined maximum or minimum. Now, are you are you going to see a function that looks like this? I hope not, because that would mean that you have some crazy function, some absolutely crazy function at f of x. But is this test a horrible test? Yes, absolutely terrible. The biggest thing is you got to remember when you apply the second derivative test, the results are counterintuitive. A negative answer gives you a maximum, and a positive answer gives you a minimum. So that whole counterintuitive thing that is all over math, it works. It's in play here. Now, for this, we need to go to the first derivative test, or even to the graph. Could it be a maximum? Absolutely. Could it be a minimum? Absolutely. But for some strange reason, the second derivative test is clouded at this point. It's like the Force. The dark side clouds everything. Calculus clouds everything. So, it just so happens that this one's in the cloud. These are nice and clear. This one's cloudy. It happens. If it's equal to 0, it's cloudy. If it's positive, it's a minimum. If it's negative, it's maximum. If it's 0, it's cloudy. You just can't tell. Any questions? Make sense-ish? Alright. Cool. Very cool.